ASK Aviation School.
Welcome to ASK Aviation School.
Today, we are going to understand the Airbus A320 air conditioning system in a simple and practical way. Disclaimer: system details may vary with aircraft MSN and configuration. This material is for general guidance and understanding only.
Now, this is way more than just about comfort. It's a really critical piece of engineering, and we're going to see exactly how it all works. We're going to break this system down so you know it inside and out, long before you're sitting in the pilot's seat.
At 35,000 feet, the atmosphere is entirely hostile to human biology. The outside air pressure is insufficient to oxygenate blood, and the ambient temperature hovers around -55°C. To create a survivable cabin environment, commercial aircraft like the Airbus A320 extract high-pressure bleed air directly from the compressor stages of the main engines. This provides the necessary pressure, but the air enters the pneumatic system exceeding 200°C at over 32 psi.
I mean, that's hot enough to cook with. So how in the world does the airplane take that inferno and turn it into the nice, cool 24 degrees you punch into the controls? Well, that's the magic we're going to unpack today.
Before that air can reach the passengers, the system must drop the temperature from 200 degrees down to a comfortable 20 degrees. This extreme thermal reduction must happen without the use of chemical refrigerants like Freon, relying instead on the physical properties of the air itself. The environmental control system, classified under ATA Chapter 21, accomplishes this across three distinct phases. First, air generation via engine bleed. Second, conditioning through the air conditioning packs. And third, pressurization, regulated by the rear outflow valve. The conditioning phase relies on thermodynamics. The air cycle machine strips heat from the bleed air through a sequence of mechanical compression and rapid expansion. Once cooled, the distribution phase hands control over to digital logic. The air conditioning system controllers, or ACSCs, route and mix that air to satisfy the specific temperature demands of different cabin zones. This schematic maps out the architecture solving that problem. It maintains temperatures in three independently controlled areas. At the top, conditioned air is routed to the cockpit, forward cabin, and aft cabin. Each zone holds a distinct temperature setting simultaneously. But how exactly does the aircraft generate this conditioned air in the first place? And where is that air actually coming from? The cooling process begins when hot bleed air is routed into the primary heat exchanger. Here, outside ambient ram air acts as a heat sink, absorbing thermal energy and bringing the bleed air temperature down. The system then routes the air into a compressor, which increases both its pressure and its temperature. Point 0 to 1A shows the compression stage, widening the temperature differential to help the main heat exchanger dump thermal energy. From 1A to 2A, ram air strips away heat. The 4A to 4B drop represents the turbine lowering temperatures to near freezing. The energy extracted by the turbine is transferred via a common shaft to drive the bootstrap compressor, closing the mechanical loop of the cycle. This schematic shows the sources of high-pressure air that feed the architecture. At the bottom, air is supplied by Engine 1 and Engine 2 bleed, the APU bleed, or a ground high-pressure connection. This bleed air leaves the engines at hundreds of degrees. How does the system drop those temperatures into the freezing range? Cooling occurs in the air conditioning pack's air cycle machine. Warm bleed air enters the primary heat exchanger. The compressor squeezes this air, raising its pressure and temperature. It enters the main heat exchanger for more cooling. Finally, turbine expansion creates a freezing discharge. Because this rapid temperature drop forces water vapor to condense, the air must be routed through a high-pressure water separator before hitting the turbine. If the moisture is not extracted, ice crystals will form and physically damage the turbine blades. If both packs output freezing air, how do the cockpit, forward cabin, and aft cabin maintain different selected temperatures?
All right, so the packs have worked their magic, and now we've got a steady stream of super cold air. But we don't want to turn the cabin into a freezer, so the next job is all about fine-tuning that air for those three zones. Before that frigid air even gets to the cabin, it goes into a mixing unit, and in there, it gets mixed with air that's been pulled out of the cabin and run through some really good filters. This is such a smart design because it means the engines don't have to supply 100% brand new air all the time, which reduces how much bleed air we need, and, this is the important part, it saves fuel. So this is a really important concept to grasp. temperature control is basically a two-stage process. Think of it like a faucet. The packs are the cold tap. They just provide a constant supply of very cold air. Then you have these things called trim air valves. They're the hot tap. They add back tiny, precise amounts of hot bleed air to mix in and nail the exact temperature you selected for each zone.
This chart illustrates the system's operating logic. The zone controller calculates the demands for all three zones, and the air conditioning system controller forces both packs to supply an outlet temperature cold enough to satisfy whichever single zone has the lowest demanded temperature. The trim air system adds heat to satisfy different zones. In this schematic, hot bleed air bypasses packs via green lines. The mixer unit combines freezing pack air with recirculated cabin air. Hot trim air then injects into this cold mixture to warm each zone.
So I know what you're thinking. This whole thing sounds incredibly automatic. And it is. But you, as the flight crew, still have a say. Let's head up to the flight deck and look at the controls you'll actually be using.
This air-conned overhead panel is the primary interface. At the top, the crew uses 3 dials to select target temperatures from 18 to 30 degrees Celsius.
So your main job is right here with these 3 knobs: cockpit, forward cabin, aft cabin. You just dial in the temperature you want, say anywhere from a chilly 18 degrees Celsius to a warm 30, and the computers take it from there. Now this pack flow selector, this is where you really see that balance between comfort and efficiency. You're essentially telling the system how hard to work. Got a light passenger load on a cool day? Set it to low and save some fuel. Full flight, middle of summer? You're going to want a high for maximum performance. It's all about giving the system what it needs and nothing more. Okay, last section. Let's talk about the brains of this whole operation, and more importantly, what happens when things don't go according to plan. This is one smart, tough system. The whole show is run by a pair of computers called the Air Conditioning System Controllers, or ACSCs for short. They're constantly watching the temperatures, checking them against what you've selected, and telling all those valves and fans what to do. It's totally seamless. But what if? What if one of those really important parts, like that air cycle machine, just gives up? Does the whole cabin turn into an oven? Nope, not even close. See, this system is designed with layers and layers of safety nets. One computer lane fails, no big deal. The other one just takes over. No one even notices. The ACM seizes up, the pack is smart enough to just bypass it. You won't get maximum cooling, but you'll still get cooling. It's called graceful degradation. The system is smart enough to keep working in a limited way instead of just quitting. That's the sign of a safe, well-designed aircraft.
To monitor the operation digitally, the crew references this ECAM cond page. These green arrows represent the real-time position of the zone trim air valves, modulating between cold and hot. If a physical valve fails, the green arrow is replaced by amber crosses. Additionally, this ECAM bleed page shows the actual pack flow rates, compressor outlet temperatures, and the pack turbine bypass valve positions. The ECAM system takes complex thermodynamic machinery and abstracts it into simple, actionable visual data for the crew. What happens in a worst-case scenario? If both packs fail, or if smoke needs to be cleared from the cabin, how does the aircraft breathe? When the normal cooling hardware fails, the system relies on the mechanical failsafe, the emergency ram air system. An emergency ram air inlet opens, routing ambient air straight through this valve and directly into the mixing unit to ventilate the cockpit and cabin. There is a strict pressure limitation here. The outflow valve will only automatically open 50% to allow this ram air circulation if the cabin differential pressure is less than 1 psi. The system also uses automated logic to maintain airflow volumes. If you are operating on a single pack, or if the APU is supplying the bleed air, the system automatically commands a high flow rate, regardless of the crew's manual selection.
And that brings us right to the end, and to a really important question for you. This system is almost completely automatic. It fixes itself. It adapts. So what's your most important job as a pilot? It's not just about turning the dials. It's about understanding how it thinks, knowing what it's going to do next, especially when things go wrong. It's about being the true master of the machine, even when it's running itself.
To recap, the A320 uses highly automated controllers to extract hot bleed air, drop its temperature in the packs, and perfectly trim it with hot air to maintain 3 independent zones. Thank you for watching, and kindly subscribe, like, and share this video. Through a combination of layered automation and mechanical failsafes, the system keeps the internal atmosphere stable, even at the limits of the flight envelope.
ASK Aviation School.